Hello and welcome. Bill Judge at Monkworkz here. This is the third video in a series I promised to you guys to detail. Initially, just an introduction to the device, and I did a bench demo, and now finally this is the installation and operation type details. So hopefully this will be illuminating for you guys. If this is the first video that you've seen, you should probably check out the earlier videos. This one's going to be quite long, and lots and lots of details on how it works, how it could work in your airplane, some installation tips, that sort of thing. So check out the other videos first, but if you've seen those and you're looking for more details, you're looking for a jump start on the manual, I highly recommend you sit through this. And it's not a replacement for either manual, but it will give you a jump start on that. So anyhow, without further ado, this is the presentation I gave at Oshkosh, so I'll run through my initial bio here quickly. Electrical engineer, RV8 builder and pilot, about 1,500 hours, 1,550 hours on my RV8 now, 2,500 hours total time. Done some backcountry flying and flying in Canada, Caribbean, Baja, lots of places where you don't want to get stuck without having an electrical power source, and you don't want to have to do any kind of in-the-field repairs. And I'm motivated to make lightweight, reliable, compact electrical power systems for experimental aircraft. And foot stomp that, experimental aircraft only here, nothing for certified planes. So, move it along if you're not an experimental guy. If you want to get a hold of me, Bill at monkworkz.com works great. Would love to hear from you. So, some briefing notes, some disclaimers, just to let you know what you're getting into here and set the expectations. This is for experimental aircraft only. So, as I said earlier, store-bought airplanes need not apply. This briefing supplements, it doesn't replace the manual. So check out the installation manual online. And this briefing doesn't qualify you for anything other than being able to put up with a dull presentation from a lackluster briefer, this guy. It's not a replacement for learning and understanding best practices of aircraft electrical wiring, aircraft electrical systems. And if you're looking for more details about that, I'd recommend you check out Bob Knuckles' content. The Air Electric Connection, his writing and the forum are just fantastic sources for learning about how to best set up your airplane for whatever it is your mission is. And I can't tell you that. I might later on have some suggestions, but for now, I think you guys got to make your own best decisions on that. So. And down that vein, this presentation says nothing about what it takes to build a well thought out, reliable electrical system, which in my opinion is an absolute requirement for safe flight in many of the experimental aircraft that we fly. I've got dual electronic ignition, I've got a Garmin 430, I've got a glass panel. All those things are electrically driven, and if you don't have power, then that means you're in a bad way. So anyhow, diving right in. Let's talk about how we make electrical power. And I know this sounds like we're starting at the very basics here, but this will give you a better idea of how the device works and let you better understand how it can be used for you in your airplane. So at a real fundamental level, we're talking high school physics or maybe even earlier in your schooling. You take a loop of wire, as shown in this picture here, and rotate that loop of wire in the presence of a magnetic field. So the magnetic field is going from south to north there. You rotate the wire, and the magnetic field is developed across the wire initially, and then as it rotates, the magnetic field isn't influencing the wire, and then it influences again, but in the opposite direction. And what happens here is the change in the magnetic field induces a voltage in the wire. So that's where you get your voltage from. And if you rotate the wire faster, then you'll get more voltage, or if you put it in a stronger magnetic field, you'll also have a higher voltage. And faster rotation and stronger magnetic field means that there's more current, more voltage, more power available. And another interesting tidbit here is if no current flows, there's very little resistance, practically none, theoretically none, to the rotation. But once you actually allow current to flow, then the loop of wire will resist rotation. And if you get a hold of one of my generators, you can demo this really easily. The outside of this thing spins, it's an outrunner, and you can sit here in your hands and spin it. And it'll run for a couple rotations. But if you put the wires together, then it will no longer rotate easily. It actually is resisting my rotation here with my hands. So, if you're not pulling power out of this device, there's really no parasitic drain, parasitic load on your aircraft. So anyhow, that's the basics. But if we're actually making power for our airplane, we're not talking about loops of wire and spinning them and that sort of thing. How do we really make power? And I think the most common solution in our small airplanes is an alternator here. And this is an automotive alternator. A lot of the alternators we run in aircraft have been adapted from the automotive industry, and that's fine. They work great. No real issues, with that. There's some upsides and downsides, but the explanation of how this thing works is what I want to get to here. So how do we commonly think of how this thing works? So AC is rectified into DC. That's what we're told, right? And there's not many more details than that. It's just like, hey, alternators work a lot better because somehow they take AC and it's rectified into DC, and then that is somehow superior. So another way that we've generated power in electrical power in aircraft is the generator here. So this is a generator from like an O200, 10-pound generator that maybe puts out 25 amps on its best day. And then nothing on the ground. Like when you're at idle, you're not seeing any kind of power out of this device. And then what we're told about this thing is this is the old school way of doing it. DC is output directly, and that's the end of the explanation there too again. But what people have experienced with these things is unless you're in cruise, you're not seeing any power. And you can literally see your lights get brighter when you push a throttle in on takeoff in an airplane equipped with one of these. And not the best solution for you, the variation in voltage regulation there. So anyhow, moving along, I threw this in here because I think it illustrates how our nomenclature may or may not really serve us that well here. This thing is obviously a generator, right? This is one of these pull start type generators. And we call it a generator, right? But it's putting out alternating current. So the idea that our alternator that's in our airplane, that AC is somehow making it work better, it kind of falls apart when you're like, okay, this is a generator, but it puts out AC. So AC is output directly from this device. And that's kind of the end of the explanation there of how those work. If we dig in a little bit deeper and we want to talk about how is the voltage regulated out of these devices, the magnetic field inside the alternator actually changes, and that's what's controlling the output from this device. So the previous slide, I mentioned, hey, if you're able to change that magnetic field, then lo and behold, you're going to get different output. So what happens is the field wire that's in these alternators, the field lead, is modulated in current. So they'll send more current to the field lead in the event that you need more current out, and then less current if you need less current out. And there's a limit to this. The field has an upper limit for how much current it can pass, and then the other limitation is how fast you're rotating the alternator. But that's how an alternator regulates the voltage in your airplane, is when you're at a lower RPM and you need more current, it sends more voltage, more current through the field, making a stronger magnetic field, which then makes more power output. And as you push the throttle in on takeoff, the RPM goes up, power starts ramping up out of the alternator, and the regulator automatically starts to reduce the field current, reduce that magnetic field that's inside the alternator, and you make the same amount of power, but with less field current. So there's that seesaw relationship there between the field current and the RPM. How do we regulate voltage out of these old school generators? I mentioned this already. There is no low RPM output on these things. And then the regulation means that comes in, you're at 2700 RPM on takeoff, and this thing's putting out actually more voltage now than you need. That excess voltage is literally burned off. You have the very old school way to do this is a pile of carbon, a carbon pile regulator, where when the voltage gets higher, there's an electromagnet that squeezes the carbon pile, and it conducts more electricity, and the voltage is dragged down by that. So all that energy that the generator is making is dumped out in heat, which is obviously undesirable. Okay, And finally, our campsite generator, RPM is constant out of this thing. And it's got permanent magnets, so the magnetic field doesn't change, and the RPM is constant. If you notice these things, when you pull the pull start, it spins right up to whatever RPM it's set to run. A lot of times, just because of how the math works out with 60 cycles, 60 hertz, is 3,600 RPM or 1,800 RPM or some kind of multiple of hertz times 60 for seconds. So 3,600 is a real common RPM for these type things. And the RPM sets the voltage, and it also sets the cycles that your AC equipment needs to run off of. So there's really no regulation necessary here from the voltage perspective. And then as you draw more and more current out of these things, it starts to drag the RPM down, and that's when the max capacity of the generator has been reached. So, what is this gadget that Monkworkz is offering here? This is similar to your alternator. AC is rectified into DC. So three-phase AC comes out of the generator and goes into the regulator, and it turns into DC. And the way the voltage is regulated is I'm efficiently converting the voltage into what your airplane needs, and doing this in real time. As the voltage changes, the regulator is changing how it's regulating the output. And this voltage conversion has traditionally been difficult to do, but modern power electronics allow me to do it in a compact, efficient manner. So you're not wasting very much power. You're still getting a ton of power out, 30 amps. And the permanent magnet setup here allows you to create power independent of whatever else is attached to your airplane. So you don't need any phantom current. The field current, it just doesn't exist on this device. I consider it a generator. Plenty of people are calling it an alternator. Call me anything you want. Don't call me late for dinner. If you want to call it an alternator, that's fine. But technically, I think it's a generator. It's closer to what we would consider a generator, of everything on this page here. It's just how are we regulating the voltage out is the difference. So I think I've covered some of this here already, but why would you want one of these? I mean, for me, the number one was I wanted electrical redundancy. I didn't want to have any compromises in being able to get home. I wanted a backup capability that could power everything in my airplane. And just as a reference, I flew my airplane to Oshkosh and back. I solely ran on my generator, 30 amp generator. I also ran an oxygen concentrator that chews up about 20 amps. So all my loads in my airplane are 10 to 12 amps, and then the oxygen concentrator was chewing up 15 to 20 amps there as well. So this thing was completely at its max output for the entire trip to Oshkosh and back, 18, 20 hours, and ran no problem. So I can power everything I need just on it. So as a secondary power source, this is not just limp to your destination capability, but get you all the way there, get you on to whatever your next place is, and get you home. It's compact. That's another point here. It's about a ½ inch shorter than anything else that will run in the vacuum pad, and that's a big bonus for a lot of airplanes that don't have a lot of space between the firewall and the engine. The Pitts specials that have a 540 in them, several of them I'm aware of, you need to remove the engine mount to get some of the other vacuum pad mounted devices in there. You need to remove the engine from the mount to get you space to put it in so you can get around the studs. And with a ½ inch less space off the face of the vacuum pad, that gives you more room to install it. The diameter is a lot smaller too than other devices out there. So it's compact. I think the installation is simple. We'll get into more installation details here, but for me, I think the installation is very straightforward, and you can add complexity, but depending upon what your goals are, you can do this pretty simply. What is it? I think it's a permanent magnet generator. I kind of harped on this a little bit already. It is an outrunner in that the outside of the generator rotates. So, for whatever reference that's good for you or not, you do need to make sure that whatever is underneath your cowling and in the neighborhood of this device doesn't touch it, because, like I said, the outside rotates. 2.6 pounds all up weight between the regulator and the generator and all the accessories you'd bring with it. It's for Lycoming engines, but we've got Continental ones out there as well. Just the generator's wound a little bit differently and the regulator's programmed a little bit differently, but they look identical. They're exactly the same, in form factor, just slightly different winding and slightly different programming. And we've done 28 volt ones as well. So if you got a 28 volt system, we can set you up, and it's going to be half power, but still not half power, half the current, same amount of power out of the 28 volt ones. Features, kind of went over the first one there, compact design. It's got a purpose-built shear coupling. If you look at the size of the shear coupling, it's tiny compared to a traditional vacuum pad, which is about another inch off of here. And that's where we're picking up some of the space that makes this thing so compact. It's got a slow start feature in the regulator. So what that means is that when it comes online and starts trying to provide power to your bus, it doesn't go to full power right away. It spreads out that ramp up over a period of time so that it doesn't snap the shear coupling. That's a failure mode that's been established in some of these other systems where you have a vacuum pad backup and it all of a sudden ramps up to its full power and it snaps the shear coupling, and now you don't have any power source. So something to keep in mind when you're working on your electrical system. It's completely self-exciting, so you spin it, you get power out. There's no phantom current needed. There's an enable wire, so you set up the enable wire and you get power out if you're spinning it fast enough and it's within temperature limits and everything is functioning right. It has a status light that you can run off of it. Essentially, it's one of the pins on here, pin number 2. You connect that to your 12 volt bus through with an LED in series with a resistor, and it'll turn that LED on and off by grounding it or not grounding it and letting you know whether or not it's working and how well it's working, basically. It's got an onboard fuse, barely visible here, but like the size of a grain of rice. It's got an output fuse that's rated for 30 amps, which replaces a need for one of these A&L type fuses. This thing is just massive. It's rated for 600 volts, and if you ever see 600 volts in your airplane and it's not associated with your ignition system, you're doing something wrong. So I think these things are really excessive. I have had one in my airplane, and I don't know why this has become the de facto, but it's way overkill. So anyhow, no need for an A&L fuse. It's got a current shunt on board, and it's basically just reading the voltage across that same fuse that's on the output, and you can use that to drive a traditional current shunt type display. And the final feature that I'll run through and touch on several times through this brief is that, I'm calling it here on this slide, intelligent cooperation with other power sources. So it will sit back and wait for a compelling need. I define, through the programming of the device, the compelling need is your bus is below 13.7 volts. If it's below 13.7, then it starts trying to make power. If you're spinning it fast enough, it will try and bring that bus voltage up to whatever setting you've got it set for, 14.2 volts or 14.6 volts. If your bus voltage is at 14 volts, then it's not going to try and provide power. And this is a measure to try and keep it from interfering with any other power sources that are on your bus. So anyhow, we'll talk more about how that functionality works. So generator installation considerations. You need a vacuum pad. So, Continental, Lycoming, whatever, like that's the base need here. And in a Lycoming context, it's the rotation speed is 1.3 times the crankshaft speed. And I mentioned this already. Continentals and other engines are possible. You can contact us and we'll square you away for that. I've got a shot of an accessory section here, and you'll see the vacuum pad is here, but there's no housing on it. It's just the bare studs and a bare accessory section. What happens is a housing like this sits on the back of the accessory section and has a gear inside it. The gear grabs the camshaft, and if this is installed on your airplane, on your engine, the back of your engine will look something like this. If it has this housing and it has the square cover over it with the studs hanging out, chances are you've got the gear in there. If you don't, that's fine. You can go procure the gear. You can get them off of eBay. You can get them from Lycoming, get them from any number of places. but you definitely need that. And you pull this cover off here, and you torque down put the generator in, torque down the bolts. The generator needs cooling, so it's got a nipple here that the cooling duct snaps into, and that will keep the thing cool for your for every condition that we think you're going to encounter during operation. So end installation here looks something like that, and oil filters in the foreground here, but you can see it's much smaller than the oil filter. It's smaller than a Coke can, really. So that's what you have to do in order to install a generator. You need a vacuum pad, you need the gear inside of there, the housing, and I provide a gasket, and torque it all down, put on the duct, run the duct to your baffling, and that's the generator installation. All right, minimum electrical installation. This is the part that probably confuses more people than anything else in this setup here. So I'll walk through it twice here. Once with the schematic like this, and then another time with a picture. So running through the schematic here, on the very left side is the input side of the regulator. So you have 3 wires that come off the generator. These guys, I provide crimps for you. Size them to length or wherever you're going to mount the regulator itself, and then crimp them down, make sure everything is not going to move. So 3 wires going into the screw terminals on the regulator here. And then I also provide a tiny, literally, pico means small, pico lock connector here that plugs into the regulator as well. Plug that in, the input side is then done. Make sure you keep those wires from chafing anything, keep them away from the outside of the motor, the generator, pardon me. But that's essentially installation there. All right, on the output side, you've got 2 screw terminals, one's ground and one's power. So number 10 wire there, please. The device is capable of 30 amps, so number 10 wire is right at its limit at 30 amps. So, use number 10 there, nothing else. And I provide you number 10 crimps as well for those. Good quality ones, Pidge ones. We'll talk about those a little bit later. And then, off of the device, so you run that number 10 wire, the positive, over to where you're going to supply power to. You should put some kind of a fuse current limiting device there, just because there is a possibility that the wire would chafe between where it dumps power on the bus and the regulator, and you don't want that potential short from chafing to drag down your entire bus. So if that did happen, that fuse would open, and then the problem goes away. You don't have a fire, you don't have your bus dragged down, all that kind of stuff. And I'm showing here a master contactor relay integrated into the schematic here, and it's up to you what you guys put in your airplanes and how you install it, but connecting to the switch side of the contactor is the way to go. And we'll talk more about that later, but there's some parasitic load associated with this, so you don't want it on a continually hot bus. You want some kind of switching capability there, and that can be one of those CAN contactors, whatever your system is set up for. And finally, you need an enable setup. So pins 1 and 6, connect those together, and the device will be enabled. So if schematics aren't your thing, then a picture might be easier. So this is a fully functional electrical installation here. On the left side here, I've got the power wires coming in, number 12 wires coming from in this picture. They're number 14 on an older model, but they're number 12 wires now. So it'd be yellow crimps here. Got the thermistor connection. So 3 phases connect in any order. And then pre-wired thermistor plugs in the pico lock connector I mentioned on the last slide. Power and ground. So I'm coming off of the positive here. I go and hit a fuse, as I mentioned before, and then I go into a load here, which is just a light bulb in this case. So external fuse, master breaker, whatever. Just make sure that you're not putting yourself in a position where if a wire chafes through, it's going to drag down your whole electrical system. So some kind of fusing there is recommended. And finally, the load. I mentioned this already. Enable switch. So the way this switch paddle is set up right now, I've got the switches up, which means the contacts are down. So these two connect together, meaning that pins 1 and pin 6 are connected together. So it's in the enabled position right now. And don't forget the cooling duct. So you need a cooling duct both for the generator and for the regulator. So don't forget that. Mounting the regulator, put it under the cowling. It's made to put up with the temperatures under there. It needs the cooling that you have associated with your baffling. So between those two things, I highly recommend you put it under the cowling. If you don't, then you got to deal with extending the wires and finding cooling, all that sort of stuff. It's got a conformal coating on the circuit board. It wants to live there. And the two main ways I see people mounting this is directly on the firewall with number 6 screws, or mounted to the engine mounts with the dowel clamps. And the case is quite beefy, so you can just grab two of the corners of the case and use the dowel clamps with AN4 bolts. I've seen people use a tap and tap the screw holes. That works great too, so you can run screws into those without having to worry about nuts. If you do tap them, make sure that you keep all the excess shavings from your drill away from the electrical end of the things, because obviously aluminum conducts and you don't want that associated with your electrical stuff. But that works great too if you want to tap them. Just be careful with the shavings. All right, so installation tips. Number one installation tip here is you read the manual. Spend a lot of time writing it. It's got a lot of good details in there, but I'll hit some high points here. Do not connect directly to the battery. I mentioned this, but the regulator draws around 30 milliamps when it's connected to something, and that runs these blink diagnostic codes that I'll run through later in the brief that talk about that give you information about what's going on with the regulator at any given time. So don't connect it directly to the battery. You want to go to the switch side of your contactor or something that's switched. Different installations are going to vary of how you connect it, but that's enough said about that. Use best practices for aircraft wiring. So crimps with strain relief, PIDGE connectors, or heat shrink. I provide the PIDGE pre-insulated diamond grip if you really want to know what that acronym means. But what it means is there's 2 crimps going on in every one of these. You've got a strain relief crimp here. It's a little bit larger because what you want is the jacket to slide into that portion. You crimp the strain relief down on the jacket, so the mechanical load goes to the jacket of the wire. And then finally, you have a stripped section of the wire that goes into the actual crimp. And in both cases, you want to crimp these things hard enough that the copper that they're made out of starts to flow around the wire to some extent. That's really what you're after. And that will give you a reliable connection for many, many hours, provided you also provide strain relief for the wire on its route for wherever it's going to go. And in some cases, you can't use crimps, and as is the case for the enable switch here. So please, by all means, put heat shrink on there. So the heat shrink is providing the strain relief here. It's transmitting the load from the wire, not electrical load in this case, mechanical load, the mechanical load from the wire into the switch, so that as your plane's vibrating and whatnot, the wire isn't, the mechanical capability of the wire isn't actually taking that strain. It's all going to the jacket, straight over to the switch, and keeping it as immobilized as possible and preventing fatigue cracks in your wiring. I mentioned this already. Put the regulator ahead of the firewall within 15 inches of the generator. The regulator can take the heat that's under there, and you don't have to deal with extending the wires, and you need cooling and all that other stuff. So put it under the cowling. I get everybody's best intentions with saying, hey, electronics want to be behind the firewall, and that is generally true. You don't want to put your Garmin 430 up there, but this device has been designed to be able to put up with the conditions under the cowling. So treat the connectors with care. So these little Pico lock connectors, they are light and compact, but also they're delicate. So plug them in gently and put in a little bit of a maintenance loop and secure the wire to the bigger power wires. so that it doesn't have a lot of room to move around. You really want to immobilize all your wiring, but especially these, you want to actually have the wires set so that it's preloading against the connector a little bit. And one final tip is ground the enable back to the regulator. If you're running a 22 gauge wire from the regulator for the enable up to your panel for a switch, there's no reason you can't run another wire back, or just get yourself some single conductor shielded. Use the shield as the ground, use the center conductor as the enable, put the switch on the end of it, do all your heat shrink. If you run it back to the generator, there's no opportunity for ground loops or noise to tell the device to enable and disable repeatedly. It's just a better way to do it for that particular. It's a small signal, so there is some potential for interference. And the interference problems I've seen have been traced back to having a ground that isn't directly connected back to the regulator. So, for that one, don't touch anything en route from the regulator to your pilot enabled switch. Keep it completely isolated. All right, configuration. So you got two voltage settings you could run with. 14.6 volts, that's what I run in my plane, primary power. If you disconnect pin 1 on the regulator, it will drop the voltage down to 14.2 volts. And the device just reads this pin at startup, and that's the end of it. It doesn't, it's not like you can toggle that voltage on and off by coming up with a creative way to switch that pin on and off. At startup, it says, okay, am I 14.2 volts or my 14.6 volts? And that's the end of it. Why would you select one over the other? I mentioned that if you're in a backup type mode, you want to have the device sitting there ready to go, but not actually participating and doing anything with the bus. And there's always this potential that people talk about of two power generating devices getting in a fight with each other, essentially, on the bus. So if it's in this 14.2 volt mode, it will put out less current if your other power generating device is set for 14.4 or something higher than that. That other device is going to provide all the power, and the only time it's going to be putting, the regulator, the Monkworkz regulator is going to put out power is when the main power source allows the voltage to drop down to 14.2 volts. Then current will start flowing out of it. So that whole time, while the other device is generating power, the Monkworkz device knows how much current it's putting out, and if it runs for about 5 seconds with no current coming out, it goes into a quiescent mode where it's not active, and it's not going to have any potential to get in a fight with something else on your bus, and it'll get in that standby state a lot easier if you're set at 14.2 volts. That's the long and the short of it. So if you're running as a backup, you're running at 14.2 volts, it will enter that standby state a lot easier. Okay, optional connections. So, we talked about minimum connections, just what do you need to make it work. There's other connections you can put on here that will allow you to get more out of the device. So the active output one is the one I'll harp on the most here. And I put this in because some of my testers were running the device and they're like, I didn't even realize it kicked in. It was the speed with which it picks up the load. You're not going to notice anything unless you're looking at something that monitors what it's up to. So this pin 2 here pulls to ground and shows a really small resistance to ground when the device is active. And so you can use that like a switch to turn on and off an LED. I'm just showing here a particular part number from DigiKey PM3YD. It's just a color of an LED. And then you got 470 ohm resistor in series with it. So you connect it to your bus, which is at 12 to 14 volts. And the resistor slows down the current, keeps the current under what the LED can put up with, and then it goes into pin 2. So when the device is active, pin 2 becomes a ground. The device, the LED lights up, and the resistance range that runs across of hundreds of thousands of ohms down to about 1/100th of an ohm or something like that. That will also work as a contact input on a Garmin device or a Dynon device. On a Garmin device, you use the active low selection. On a Dynon device, I think it's even more straightforward than that. But anyhow, that's an input that you can use just with an LED for a real simple airplane, aerobatic airplane. I want to know whether or not the thing is doing something. You know, just buy an LED for 50 cents and you know, hook it up with an appropriate current limit resistor in series, and that works great. And then it gives you a little bit more information in that there are plenty of cases where it might be on and active, but not actually providing enough power to support your bus. So at 14 volts, it's an arbitrary threshold. If it's on and active, but your bus is below 14 volts, it's putting out as much current as it can, but that's not enough to bring your bus up to over 14 volts. It's going to flash. So that LED, if you had it hooked up, is going to flash, or the indicator that's on your Garmin or Dynon or whatever is going to flash as well. So you can use that as an indicator of like whether or not it's actually doing what you want. And that indicator should be either a heads up of I've got too much load on it, or maybe I'm just idling low and it's not able to support the load as you're taxiing out or something like that. But if you're in a situation where you're flying along and now you're running on your backup and that LED is flashing, that's your signal to load shed so that you can keep your power demand below what what the device actually is able to put out. So, at 30 amps in cruise, that's going to run most of your stuff. Pitot heat is the one debatable, whether or not you're able to run pitot heat and everything else in your airplane. But leaving out pitot heat, 30 amps should be enough for most aircraft out there. The next optional connection, I got I plus shunt, I minus shunt here. So this is the positive and negative of a shunt input on an EFIS or a traditional current meter. So I mentioned before, but it's just looking at either side of the output fuse. The fuse that I'm using here on the output side is a really stable resistance across a huge temperature range, and that means it also works perfectly well as a shunt. You're gonna have to calibrate your EFIS to take that shunt input, but you don't need to have a big honking shunt hung on your firewall anymore either, which is kind of nice. So, and a lot of EFISs only have one shunt input. So for sure on a Dynon, you can take this next pin here, the proportional current one, and run that into a general purpose input output, set up a sensor definition file, which we can provide, and it will read that proportional voltage that's coming out of pin 5, and turn that voltage into how much current the device is kicking out. So got a bunch of options here of how you could measure current coming out of it. Philosophically, the shunt here is a physical measurement that's independent from the brains of the device, whereas this proportional current here is developed by the device's own awareness of how much current it's putting out. So, depending upon what your standard is for believability with measurements, you could use either one, but they're both provided there and easy to hook up to EFISs. So finally, let's talk about operational flow. So I got a flow chart here, and I'll just say one caveat or one recommendation right off the top is just leave the device enabled all the time and forget about it. If you have some kind of indication of knowing when it's active, or if it's your only source of power, then why wouldn't you run it that way? But the flow chart starts here with mechanical or electrical power. And what I mean by mechanical or electrical power is when you turn your master on and 12 volts gets sent to the power and ground here, it actually comes on when that happens, and the microprocessor inside starts thinking and processing things. And what it's primarily doing at that point that's useful to you is producing these blink codes. And there's 6 on there, and in an ideal world, you're only ever going to see blink code 3 and 4. So 3 blinks if the device is disabled. You got your enable disable switch off, and then 4 blinks if it's enabled. Whoop, turn the enable on, come around from your cockpit, look in. There's an LED here that says blink, and it should blink 4 times. The other blink codes here are thermistor is disconnected. So if you pull the thermistor, boom, you get one blink every second or so. Blink, blink, that kind of thing. If it's either been overvolted on the power cycle you're on, or it's been overvolted too many times, and when I say overvolted, it's either caused an overvoltage event or there's been an overvoltage event on your bus. And there's a whole set of sequences it goes through to try and figure out, like, is the regulator the cause of the overvoltage, or is something external to the regulator that caused the overvoltage? So the 2 blinks is the overvoltage indication, and then finally either over temp or your thermistor is shorted is number 5. So those are the blink codes. Presuming the device is either enabled or disabled, you go to the diamond here, and if it's disabled, well, it's just off and nothing's happening. If it is indeed enabled, it looks at the bus voltage, and if the bus voltage is greater than 13.7 volts, it figures, hey, your bus is in a happy place at that point. 13.7 should be above any reasonable battery voltage that you'd be able to see from either lithium or AGM type batteries. And so if the bus voltage is high enough, it just stays off. But if the bus voltage is less than 13.7, then it starts looking at the RPM. If the RPM is less than 800 RPM, and all these RPM on here are crankshaft RPM, if the bus voltage is less than 800, and it just sits out and says, I'm off. Above 800, it's going to try its best to maintain your voltage. You might get 5 amps, you might get 15 amps, but somewhere in this 800 to 1,000 range is where you're limited to 15 amps. Once the RPM is above about 1,000 RPM, you'll get 15 amps. Like right at 1,000, you can get 15 amps. You should get 15 amps. It might not be 15 amps at 14.6 volts, but fairly close to it. At 1,100 RPM, certainly 15 amps at 14.6 volts. Once you get up to 1,800 RPM, then the current limit doubles. You can get up to 30 amps, and all these are limits here. I've had this question of like, wait, the device is going to put out 30 amps no matter what? Like, no. It's going to maintain voltage up to the point of regulation, 14.2 volts, 14.6 volts, and then as you add load, eventually you're going to hit 15 amps or 30 amps, whatever the current limit is at the time, and then it starts reducing the voltage straight down to a short. So if you see my other videos, hopefully you've watched those and haven't stumbled on the ultra long one here, but I short out the regulator with a wrench, and it's still trying to maintain that same current limit, and the voltage comes all the way down to 0. And below about 10 volts, the current limit also becomes smaller and smaller. That's just a measure to prevent the device from catching on fire or causing a fire. Pushing 30 amps into a dead short all the time is not good for anybody or any of the equipment that's attached to it. So got a current limiting feature when the device goes below 10 volts. So I mean, that's kind of the operational flow here, and I've omitted a lot of stuff here. There's a self-test. So at every startup, it's got redundant means of shutting itself down. It runs through a test to make sure those redundant means are there. There's an overvoltage sequence. I kind of alluded to this a little bit before, but you have this issue if you are connected with a bus that has another power source on it. Like, how do you figure out who caused the overvoltage? So what it does is it sits out for 5 seconds, waits for 13.7 volts again, and if it sees those things happen, then it's like, okay, I'll try and provide power again. So it sits out for 5 seconds and waits for 13.7 volts. So if there was an overvolt that it caused, and you have another power source, and it's carrying the bus, then it's just going to sit out. If there was an overvoltage as your main, possibly, and it kicked itself offline, but at the same time, this device saw, the Monkworkz regulator saw the overvoltage, sits out, waits its 5 seconds, sees the bus voltage is below 13.7, it starts trying to provide power. Before it does that, it actually runs through its same self-test sequence as it does at startup, just to make sure that it's going to be able to shut itself down. I talked a little bit about the voltage selection on the other slides. So there's the voltage selection sequence, that only happens at startup when you turn on power or when you initially spin the generator. So, don't expect to be able to toggle the regulation voltage on and off from the toggle switch after you've done startup. And there's a lot of other details, and all that stuff is covered in the manual. And if you have questions about it, you're more than willing to answer questions on it. Please contact us. So let's see. I think that's it. Quick summary. This device is a little bit different, but most of the users I've had, the testers and whatnot, have used the device, and it didn't change their operations any way, shape, or form. They have a lighter weight primary power source, or they've got a backup that's basically transparent to them. They don't have to overhaul their whole electrical system and think deeply about how to worry about all the different ways that things can go badly and how to cross-connect things and whatnot. So backup or primary, 2.6 pounds all up weight off a vacuum pad. I think this is about the leading edge here in electrical power generation for experimental airplanes. So give us a call. The number's on the website. Website's here. I'll link to it in the remarks. I'll also put a link to this brief. So if you want to run through the slides and pick out questions and call me, you're more than happy to hear from you. And I hope I do. So please, by all means, give us a call. And seriously, thank you for making it this far in the brief. This is incredibly long and not exactly the most riveting material for a lot of people. So I thank you for watching, and hope I hear from you. Take care. Thanks.